would be the second electron. If I go down to sodium and magnesium, sodium would be the first electron, magnesium would be the second electron. I only have two columns in the S subshell, or in the S sublevel. So that means it can only hold up to 2 electrons because I only have 2 columns. Now, we know that the S sublevel would start on the first energy level because I know that hydrogen is part of that S sublevel, and hydrogen being part of that S sublevel is in row number 1. So I know that the energy level would just be row number 1. If I go to P, if we go to the P sublevel, if we look at the P sublevel, we see that there are 6 columns in that P sublevel. If you look at your paper, you have 3 different shapes on your paper, 3 different ways that you can orient that dumbbell shape. So I have 3 shapes on my paper. That means that I have 3 orbitals because there are 3 shapes. The maximum number of electrons, if I count each one of those elements in those 6 columns, each element represents an electron. So if I have 6 elements, or 6 columns in that row, that means that the maximum number that it can hold would be 6. So that means that each one of these drawings, I had 3 drawings, each one can hold a maximum of 2 electrons. So if I went all the way through that row, I could have 1, 2, 3, 4, 5, 6. All 6 of the elements would be represented. Let's just skip this last one for just a second. Okay, D. If I look on my paper, how many shapes of D do I have? I have 1, 2, 3, 4, 5. I have 5 shapes for D. So that means I have 5 shapes, or 5 orbitals. If I count in the D, if I count all of the D columns, I go from 21 to 30. So that means I have 10 columns, vertical columns, in the transition metals, or in the D sublevel. So since I have 10 columns, each of those elements represents an electron. So that means I can hold a maximum amount of 10 electrons in that column, or in that D sublevel. On F, now F is one that I didn't give you, and that's because it can have some really weird shapes. We don't see that there's like a pattern on what the shapes look like. I will say that F, though, has 7 shapes, so I would just want you to know that F will have 7 shapes, and it can hold a maximum of 14 electrons. If you count down here, you will count that there are 14 elements in that row, so each element will count for an electron. Okay? Now the reason that you're learning this is because we have to write something called electron configurations. An electron configuration is kind of, I can think about it like a fingerprint for a person. It tells me, it can tell or identify who I am. It's the same thing with electron configurations. An electron configuration will tell you exactly where a certain element is on the periodic table. Okay? Now there are 3 rules that govern writing electron configurations. So these are just the objectives. I'm going to skip this for just a second. Okay, the way that electrons are arranged around the nucleus of an atom, we call that its configuration, an electron's configuration. I just said there are 3 rules that are going to govern this. If we look on our periodic table here, I see that my energy level, which is the same thing as principal quantum number, I can figure that out by determining what row I'm in. So I'm in row 1, this is energy level number 1. I'm in row 2, this is energy level number 2. I'm in row 3, this is energy level number 3, or n equals 3. In row 4, energy level number 4, n equals 4. In row 5, energy level number 5, n equals 5. Okay, you get that. Now, I would like to point out, guys, that look at helium. Helium is classified as a 1s. It's in the first row, so it should make sense that we would label this as 1. But helium is the only exception in terms of like where it's located, that helium will not act like a P sublevel, it's actually going to act like an S sublevel. So we can pretend like helium would be right here, filling in this little gap or this little hole for right now. Okay? If I want to figure out, actually I want to come back to this. So we're going to come back to this in just one second.